We are beginning our unit on derivatives, and today we're doing notes 1. We're going to be covering average rate of change and the definition of derivative. There are actually two forms of the definition of derivative. We're going to cover them both today. So first of all, AROC, the average rate of change in a function over a given interval. We have had this before. We started problems with AROC back in Unit 1 of PreCalculus, and we've hit it occasionally throughout the year. It is crucial now that we know what average rate of change is. So average rate of change in a function over a given interval is always just your change in y over your change in x. Difference of the y's over the difference of our x's. This is our old, I like to say the old Algebra 1 slope. y2 minus y1 over x2 minus x1. Just your old Algebra 1 slope. Let's look at an example. Let's say that they ask us to find the average rate of change of, let's say, f of x is equal to 4x squared minus 9 on the interval, let's say from x is negative 1 to x is 3. So this is a parabola pointed up. The average rate of change from x is negative 1 to x is 3 will be the slope between the point where x is negative 1 and the point when x is 3. So envision this parabola. We're finding the slope between 2 points. That's what average rate of change is. So the average rate of change, AROC, from x is equal to negative 1 to x is equal to 3 would be, I think of it as just change in y over change in x. Since y is f here, it'll be change in f over change in x. So this will be f at 3 minus f at negative 1 divided by our difference of the x's, 3 minus negative 1. Of course, just like it was when you were in Algebra 1, you're welcome to switch these and make it f of negative 1 minus f of 3 over negative 1 minus 3. Either one is fine. I usually go with my larger x value first, but either one is definitely fine. So let's see, we need to find out what f of 3 is. If we plug 3 in for x, this will be 4 times 9, that's 36. 36 minus 9 is 27, minus, now I'm plugging negative 1 in for x. Negative 1 squared is 1, 4 times 1 is 4, minus 9 is a negative 5, all over 3 minus a negative 1, that's 3 plus 1, which is 4. 27 plus 5 is 32, 32 over 4 is 8. The average rate of change, the slope between those 2 points, is 8. Let's do one more. Let's find the average rate of change of y is equal to, get a little separation here, y is equal to sine of 3x on the interval from x is equal to, what did I note beforehand, 0 to x is equal to pi over 6. Okay, so average rate of change, that's my AROC, average rate of change. That is just delta y over delta x, and this time it is a y, so we need y at pi over 6 minus y at 0 divided by pi over 6 minus 0, change in x. Okay, y at pi over 6, if I put a pi over 6 in for x, I'm going to have sine of 3 times pi over 6. 3 times pi over 6 is pi over 2. If I put a 0 in for x, 3 times 0 is 0. So I have this. And now, what is sine of pi over 2? Sine of pi over 2, I think of the graph of sine. Sine of pi over 2 is 1. So we have 1 minus, oh, and I jumped the gun here. Sine of 0 is 0. So we have 1 minus 0 in the numerator and pi over 6 in the denominator. And that is 1 divided by pi over 6, which is 6 over pi. Okay, you can think of that as multiplying top and bottom by a 6 to get 6 over pi. Okay, and that is average rate of change. That is our AROC. Now what we're going to be talking about, we'd like to develop instant rate of change. That's average rate of change. We want instant rate of change. Instant rate of change is not going to be over a range of values. Instant rate of change is going to be the slope right at a single x value. Think of a curve. Let's think of a curve. Let me say we have this curve, a curvy curve, and average rate of change would be the rate of change between 2 points. That would be the slope between 2 points. Instant rate of change will be the slope of the tangent line right here. Okay, that would be the instant rate of change right at that x value. Let's call this x value x sub 1, and let's call this x value x sub 2. I'm going to develop what instant rate of change is. Alright, and we could, get a straight edge here, we could find the average rate of change between those. We could find the slope between those. And the slope would be whatever the slope. It would be rise over run, right? It would be rise over run. So the slope, I'm going to call that slope m. Slope m here would just be our average rate of change. It would be the change, if I call this guy f, it would be change in f over change in x. That would be f at x sub 2 minus f at x sub 1, whoops, divided by change in x, x sub 2 minus x sub 1, right? So, also, do you agree that this is definitely change in x, right? So I could replace x sub 2 with whatever x sub 1 is plus my change in x, right? So I'm going to come in here and I'm going to replace this x sub 2 with x sub 1 plus delta x. So the slope will be, this is the slope, that's our slope. The slope is now going to be f of x sub 1 plus change in x minus f of x sub 1 all over, and I think I'm going to go back to just make that delta x. So I'm just going to write that as a delta x. So that is our another way to write. It's just another way to write our average rate of change, our slope between these 2 points, right? And I'm going to come in, I'm going to rename this x sub 1, and I'm just going to call it x. So if I do that, let x is equal to x sub 1, then my slope is f of x plus delta x minus f of x all over delta x. And that is that slope, right? The average rate of change. Now, that's fine for these two, the slope between these 2 points. What I'd like to do is I'd like to move this point over here, my x sub 2. I'm going to let it move closer and closer and closer. I'm going to let this, get a different color here. I'm going to let this x sub 2 move closer and closer and closer and closer to x sub 1. As we move it closer and closer and closer, our slope of the tangent line is going to, our slope of the line, here the slope would look like that, right? Here the slope, as it moves closer and closer, we get closer and closer to the slope of that tangent line right there, right? We want to move it so close that delta x is almost 0. As we move x sub 2 closer to x sub 1, delta x is getting tinier and tinier and tinier. And we want it so close, infinitesimally close to 0. We want delta x to be so close to 0 so that we have just the slope of the tangent line. So we're going to take this equation for slope here, take that equation for slope, and we're going to let delta x go to 0. We're going to take the limit as delta x goes to 0 of that expression. And this is the instantaneous, oops, I spelled it wrong, instantaneous, if I can spell it right, rate of change. Oh my gosh. Rate of change of f with respect to x. With respect to. WRT is with respect to x. Okay? It's also the slope of the tangent line. To f for any x value. That's a huge expression for us. It's a huge definition for us. So let me write it again more formally here. Okay, this is the definition, and, well, we call that the derivative. We call the instantaneous rate of change of f the derivative. We call the slope of the tangent line to f the derivative of f. Okay, so this is the definition of derivative. Okay. The derivative of a function f of x is the limit as delta x approaches 0 of f of x plus delta x minus f of x all over delta x. That is the definition of derivative. Notation. Okay, that's quite a bit to write out every time we want to say what the derivative of a function is. So we have notation for the derivative of f. There are several of them. One is f prime of x. Okay, the derivative of f is f prime of x. It looks like a 1, but it's a little slanted. We call that the derivative of f. This is pronounced f prime of x, okay, or the derivative of f, okay. If this function was g, we would write g prime of x, h prime of x, y prime of x, right? If the function was just called y, we might say y prime of x. We might just call it y prime. We might call it dy dx. That is the derivative of y with respect to x. These are all different ways of notating the derivative, and we use the various forms for different reasons. Okay? Alrighty. So let's take a look at, and well, before I go on, this is, but let me reiterate, this is, the derivative of f is the slope of the tangent line to f. The slope of the tangent line to f. The derivative of f is also the instantaneous, let's see if I can spell it right this time, instantaneous rate of change of f. Okay? There are different ways that you can be asked questions. Sometimes they'll just say, find the derivative. Sometimes they'll say, find f prime. Sometimes they'll say, find the slope of the tangent line to f. Find the instantaneous rate of change of f. There are different ways that you can be asked these questions, so know the meaning behind these. All right? Let's take a look at an example. Let's say in this first example I say, given g of x is equal to 3x squared minus 2x, find g prime of x. Sorry for the interruption. Find g prime of x. Okay, so we're finding the derivative of g, so I'm going to set up our definition of derivative. So definition of derivative is the limit as delta x goes to 0 of, our function is g, so g of x plus delta x minus g of x all over delta x. Alright, so there's my setup, and now I want to write my expression for g of x plus delta x. So g of x plus delta x, I'm going to take my x plus delta x and I'm replacing x with x plus delta x. So I'm replacing that x with x plus delta x, that x with x plus delta x, and that x with x plus delta x. When I do that, I'm going to have, let me rewrite limit. I'm going to have 3 times x plus delta x squared minus 2 times x plus delta x. That is my g of x plus delta x. I'm going to put those in brackets to separate those slightly. Now I need to write down that minus sign. I'm going to put another a set of brackets for g of x. G of x is just 3x squared minus 2x. 3x squared minus 2x. Just like that. All divided by delta x. Okay. This may or may not be looking familiar to you yet. Let's keep on going. I'm going to square this binomial. When I square that binomial, I'm going to have x squared plus 2x times delta x plus delta x squared. Okay, I'm going to distribute the negative 2 through this set of parentheses. I'll have negative 2x minus 2 delta x. I'm going to distribute this negative through this set of parentheses. I'll have negative 3x squared plus 2x, all divided by my delta x. Okay, still combining, I'm getting to where I can combine like terms. Now I'm going to distribute the 3 through the set of parentheses. I'll have 3x squared plus 6x delta x plus delta x squared minus 2x minus 2 delta x minus 3x squared plus my 2x all divided by delta x. Okay, at this point we're going to combine like terms. If we did it correctly, everything without a delta x should cancel out. This does not have a delta x with it. It should cancel out with something else, and it does, because there's a negative 3x squared down here. They zero out. This has a delta x. This definitely has a delta x. This does not. Is there a positive 2x somewhere? Yes, there is, right back here. If there's not, you made a mistake in your either foiling or you're distributing something. Okay, it's a good way to catch yourself. This term has a delta x in it, so I know it's not going to cancel with anything. Okay. With what remains, everything else has a delta x in it. I'm going to factor it out and reduce it with this delta x on the bottom. So I'm factoring out a delta x. I have 6x left from here. I have a single delta x from here. And I have a negative 2 left from here. Okay. Now I cancel out these delta x's. And once I cancel out the delta x's, I can plug 0 in for my remaining delta x's. There's only one of them, it's right there. And when I put 0 in for that, I get 6x minus 2. And that is the derivative of 3x squared minus 2x. So that is g prime of x. Okay, let's do another one. Oh, well, and in class I will ask my kids if they recognize this process at all. Not really with the limit, but do they recognize this process? And hopefully some people will. This is our difference quotient that I've been giving you throughout the year. But I have not been using delta x. What have we been using? We've been using h's. Delta x gets a little cumbersome to keep writing, and so we oftentimes will let h be delta x, and then we can replace every delta x with h, and it just is less cumbersome. Okay, there's nothing magical about the letter h. We could let it be any letter we like, not an x, not a g in this case, but we could let it be any letter we like. It's just kind of conventional to let it be an h. So either an h or a delta x. I prefer delta x. I know it's messier, but I prefer delta x because it has meaning behind it. Delta x is change in x. And so when you just have an h there, it loses its meaning. Nobody remembers that h is the change in x, right? So I like the delta x. However, h is easier to write. So let me do one where I'm using an h instead of a delta x. Let's do another example. Let's say we're given h of x is 1 over x plus 1. And the directions say to find the slope of the tangent line to the graph of y equals h of x in terms of x. In terms of x. Okay. So, slope of the tangent line, we have to know that is the derivative. That is the derivative. So we are finding the derivative. So I'm going to set up my limit. The limit as, and this time instead of saying delta x, I'm going to say h. H is going to 0. So I'm replacing my delta x with h, and I will have h of, that's going to be confusing. Let's not call this guy h. Let's call this guy f. All right, let's call this guy f. I don't want you to get confused with the h's. So f of x plus h minus f of x all over h. So I took my definition of derivative and I just replaced every delta x with an h. All right, and I want you to think of this numerator. That's just change in y. All that is change in y. On the bottom, it's change in x. It's still our old AROC, our average rate of change, our old Algebra 1 slope, change in y, change in x's. The only thing that's different is now we're letting the change in x go to 0. Okay? All right, so for f of x plus h, I'm going to replace that x with an x plus h. I'm going to replace this x with x plus h. I'll have 1 over x plus h plus 1 minus, there's that minus, f of x. Well, f of x is just 1 over x plus 1, all divided by h. Okay? For this one, if I just plug in 0 for h, I'll get 1 over x plus 1 minus 1 over x plus 1. That's 0 over 0. We have a whole and we need to cancel it out, right? So what are we going to do to cancel it out? I'm going to multiply both top and bottom by the little denominators, so the x plus h plus 1 and multiplied by the x plus 1. For this first term, the x plus h plus 1 will cancel with this x plus h plus 1. I'll be left with 1 times x plus 1 minus this 1 times, okay, the x plus 1's cancel, and I'm left with x plus h plus 1, all divided by, and in the denominator we do not distribute, we just leave it, because if you distribute you're going to have to turn around and factor, and that might be difficult to factor. So we have in our numerator x plus 1, and we have minus x minus h minus 1 all over this. I'm not changing this. Okay. Anything without an h should cancel here. X, negative x, 1, negative 1. I'm left with a negative h on top and an h on the bottom. I'm going to reduce that h, but I'm still left with negative 1, right? So I have a negative 1 on top. After I reduce out this h, though, I can go ahead and plug in 0 for any remaining h's. So the remaining h is right here, so I'll have x plus 1 times x plus 1, and this would be negative 1 over x plus 1 squared. That is f prime of x, the derivative of f. The instantaneous rate of change of f, the slope of the tangent line to f at any x value we like. All right. Okay, now I'd like to, so that's the definition of derivative, a couple of examples with that. Okay, now I would like to go back to our little curve. Okay, go back to our little curve, and I'm going to call this x value, instead of calling it x sub 1 now, I'm going to call that a. And I'm going to call this x value just plain old x. Okay? And again, I know that the slope of the secant line here, the slope between those two, that slope, call it m, that slope would be change in y over change in x, and if this curve is f of x, that would be change in f over change in x, slope, That would be f at x minus f at a, all divided by x minus a, the difference of the x's. Yeah? So that is the slope between these 2 points. Now I'm going to let x get closer and closer and closer and closer, infinitesimally close to a. If I do that, we will have the slope of the line tangent right at this a value. So we're letting x get closer and closer and closer to a. So it's going to be the limit as x approaches a of this expression. It's another way to say the slope of the tangent line. This way is fantastic if you have a number, if you know the number right there. Okay, so this is the alternative. Let me write that down. Okay, this is what we call the alternative definition of derivative. Okay, it is only valid at the point where x is equal to a. This would be f prime at a, not f prime of x, f prime of a. It's only good right at a number for x. Okay, let us do an example of that. Okay, an example for alternative definition of derivative. Let's say that I give you that f of x is equal to 2x squared plus 4x minus 3. And the directions say to find f prime right at 2. If I'm not asked to find f prime of x, I'm only asked to find f prime of 2, I would use my alternative form of the definition of derivative. So I'm going to set up the limit as, okay, the limit as x approaches 2 of f of x minus f of 2 all over x minus 2. So I'm just replacing this a, all of the a's with 2. Okay, this will be f prime of 2. Okay, so this is the limit as x approaches 2 of f of x. I know what f of x is here. Minus f of 2. F of 2. Let's come up here, and I'm going to come up here and find f of 2. Little scratch work to find f of 2. F of 2 is 2 times 4 plus 4 times 2 minus 3. 16 minus 3 is 13. So I will put that 13 there because that is f of 2. All divided by x minus 2. This is the limit as x approaches 2 of 2x squared plus 4x minus 16 all over x minus 2. Okay, time to factor. And how do I know it's going to factor? Every one of these will. Okay, you can always do that with these. So I see I have a common 2. Everything has a 2, so I'm going to make my life a little easier and factor out a 2. Okay. All right, keep on factoring. X and x. I know it's going to have a minus 2. I know it will. 2 times 4 is 8. I need a plus back here. I make sure positive 4x minus 2x is positive 2x, but I know it's going to have that x minus 2 in there because of that guy right there. There's your whole. We found our whole. They cancel each other out. We're going to plug 2 into the remaining x, and we'll have 2 times 6, which is 12. So the slope of the tangent line to f when x is 2 is 12. That is f prime of 2, the derivative of f at 2. Let's do one more. Okay, let's say that we are given if y is equal to 2x cubed plus 1, find the instantaneous rate of change of y with respect to x when x is equal to 3. Okay? Alrighty. So let's do this. Instantaneous rate of change is another way to say derivative. That's derivative. So we just want the derivative of y with respect to x when x is 3. Since they're saying when x is 3, I'm going to use the alternative form of the definition of derivative. Okay, so limit as x approaches, x is approaching 3, and now I write my change in y over change in x. So this is going to be I'm going to write this down again. F of x minus f of a, where a is 3, so f of 3, all over x minus 3. Okay? My f of x is just my y. So that'll be 2x cubed plus 1. Okay? Minus, now I need my f of 3. Time to come up here and do some scratch work. Y at 3 will be 2 times 3 cubed. 3 cubed is 27 plus 1. 2 times 27 is 54, plus 1 is 55. So we have 55 right there. Okay, all over x minus 3. Let's simplify this. We have 2x cubed minus 54 over x minus 3. Time to factor. I see that I have 2 even numbers, so I'm going to take out a 2. And now I have a difference of cubes that I can factor into a binomial and a trinomial. When I factor that, I'm going to get x minus 3 as my binomial. I knew that would be there, by the way. For my trinomial, square the x, multiply these two together, change your sign, and then plus 9, plus the square of 3. This is always positive. All divided by x minus 3. We found our whole. We can cancel it out. Plug 3 into the remaining x's. We will have 2 times 9 plus 9 plus 9. That is 2 times 27, or 54. So that is y prime at 3. That would be the notation for that. Y prime at 3. That is a very steep slope. Up 54 over 1. That's a steep slope. Do you agree? 54 over 1. Alrighty. That is average rate of change, Where's my note? Where are my notes here? That is average rate of change and the two versions of the definition of derivative.